Virtual particles borrow energy for 10⁻⁴ seconds before vanishing. A 2020 University of Tokyo study confirmed their measurable Casimir effect force. Your body right now is emitting virtual photons that interact with empty space. Richard Feynman first mapped this invisible world in 1949 on a napkin. He called them virtual particles, and they were never meant to be taken literally. They were bookkeeping tools, mathematical ghosts that helped him calculate how real particles interact. In 1935, it is polarized. Virtual electron-positron pairs flickering in and out of existence create a screening effect. This was the first hint that the vacuum is alive. His diagrams, published in Physical Review in 1949, showed particles exchanging invisible messengers. That photon is absorbed by another electron. A force. A repulsion. But the photon itself, it never appears on any detector. It violates energy conservation for a time shorter than the uncertainty principle allows. It borrows energy from the vacuum and repays it before anyone notices. This is the quieter truth about virtual particles. They are disturbances in the underlying quantum field. No ripples, no wind. That is the classical vacuum. Now imagine that pond at every point on its surface is trembling. Not with waves you can see, but with microscopic vibrations so small and fast that they exist for less than the time it takes light to cross an atom. Virtual particles are the names we give to those vibrations when they become energetic enough to briefly mimic a real particle. They are events. They are the quantum field doing what quantum fields do, fluctuating. The Heisenberg uncertainty principle is the legal framework that permits this theft. The relation delta E, delta T, delta T. The more massive the particle you want to create, the shorter its borrowed lifetime. A virtual electron with a mass of 511 keV, a virtual top quark with a mass 350,000 times larger, vanishes almost instantly. It only cares about the balance sheet, and this is where the debate begins. Some physicists argue that virtual particles are not real. They are artifacts of perturbation theory, a mathematical trick used to approximate interactions in quantum field theory. Others point to measurable effects. The Casimir effect, first predicted by Hendrik Casimir in 1948. The only way to calculate that force accurately is to sum over the virtual particle modes between the plates. The Lamb shift, measured by Willis Lamb in 1947, shows a tiny shift in the energy levels of hydrogen caused by the electron interacting with its own cloud of virtual particles. The Uehling effect, calculated in 1935, shifts the energy levels of muonic atoms. They are real. They change the structure of atoms. They move mirrors. But when researchers looked closer, the Brookhaven National Laboratory experiment, published in Nature by the STAR collaboration at the Relativistic Heavy Ion Collider. Specifically, it looked at lambda and antilambda particles, heavier cousins of the proton and neutron, produced in high-energy collisions of gold nuclei. The spins were aligned. And the only explanation is that these real detectable particles inherited their spin alignment from virtual quark-antiquark pairs. This is the quieter truth. Virtual particles are not just mathematical ghosts haunting our equations. They leave fingerprints on real matter. The Antilambda contains a strange antiquark. In the vacuum, strange quark-antiquark pairs are always spin-aligned, a consequence of the strong force and the quantum numbers of the vacuum state. When a collision provides enough energy to boost these virtual pairs into real particles, the invisible becomes visible. The experiment at RHIC did something remarkable. It used the collision itself as a microscope. By smashing gold nuclei at energies approaching the speed of light, the STAR collaboration created a tiny fireball hot enough to liberate quarks and gluons from their confinement inside protons and neutrons. In that fireball, virtual particles from the surrounding vacuum received the energy boost they needed to become real. The team then tracked the decay products of the lambda and antilambda particles. The correlation was clear. It matched the prediction for particles born from a spin-aligned vacuum. It is not the Lamb shift. It is a direct experimental link between virtual particles in the vacuum and real particles in a detector. The vacuum, it turns out, is not a passive backdrop. And this raises a deeper question. If virtual particles can become real when given enough energy, the uncertainty principle allows them to exist for a fleeting moment. It can turn a temporary fluctuation into a permanent particle. It is a threshold. Cross it, and the ghost becomes flesh. The theoretical framework behind this is called quantum field theory. In QFT, the electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field. The vacuum is the state where all fields are in their lowest possible energy configuration. But that lowest energy is not zero. Virtual particles are the temporary excitations that appear and disappear within the limits set by the uncertainty principle. What the RHIC experiment shows is that the field can succeed. Given enough energy from a collision, a virtual excitation can become a real particle. The vacuum donates its fluctuations to the fireball, and the fireball returns them. It is transformation. The energy of the collision is converted into mass, and the vacuum provides the template, the spin, the flavor, the quantum numbers that define what kind of particle emerges. The philosophical implications are staggering. If the vacuum contains virtual copies of every particle that can exist, it is a warehouse of potential. Every electron, every quark, every neutrino that has ever existed or will ever exist, they are not there, but they could be. Given the right conditions, they will be. This is the quieter truth about virtual particles near the vacuum line. They are not anomalies. They are not errors in our mathematics. They are the quantum field breathing. And we have finally learned to hear the breath. The breath of the quantum field is not a metaphor. It is a measurable phenomenon. And the star collaboration at RHIC measured it in 2023 by tracking the decay of lambda particles. To understand what they saw, you must first understand what a lambda particle is. It is a baryon. When a lambda decays, it transforms into a proton and a pion. This is not guesswork. The decay products remember the parent's orientation. The team at Brookhaven smashed gold nuclei together at energies exceeding 200 gigaelectron volts per nucleon pair. The collision temperature reached trillions of degrees, hot enough to melt the boundaries between quarks and gluons. Virtual particles that normally flicker and vanish in isolation suddenly found themselves in a bath of energy. They could become real. What the star collaboration measured was the spin correlation between lambda. The correlation was not zero. The spins pointed in the same direction, and the only way to explain that alignment, strange quark-antiquark pairs in the quantum vacuum are always spin-aligned because of the strong force and the Pauli exclusion principle. The vacuum does not just influence matter, it imprints its quantum state onto it. This is fundamentally different from the Casimir effect. The Casimir effect measures a force. It tells you that virtual particles exist between two plates, but it does not tell you what those particles are. It isolates strange quarks. It connects a virtual fluctuation in the vacuum to a real particle in a detector. With a specific flavor, it is a direct correlation. The implications for quantum field theory are profound. In standard perturbation theory, virtual particles are internal lines in Feynman diagrams. They are summed over. They disappear in the final calculation. But the RHIC experiment demonstrates that virtual particles leave observable imprints on real particles that survive the collision. It persists. This means the vacuum state is not a passive backdrop. It is a structured medium with its own quantum numbers and correlations. The experiment also resolves a long-standing tension in how physicists talk about virtual particles. Some argue they are merely mathematical artifacts. Others insist they are real because of measurable effects. The RHIC data tilts the balance toward reality. If virtual particles were only bookkeeping tools, the alignment is a physical effect. It requires a physical cause. The vacuum is that cause, but the quieter truth is even stranger. The vacuum does not contain virtual particles in the same way a box contains marbles. It contains potential, correlations between quantum fields that can be activated under the right conditions. The spin alignment of strange quark-antiquark pairs exists in the vacuum as a correlation. When energy is added, that relationship becomes a particle. It is a tendency, a predisposition, a quantum inclination. This is why the word virtual is both useful and misleading. It suggests something less real than a real particle. But the spin correlation measured at RHIC, the virtual particle is not a ghost. Given energy, it grows into a real particle. The collision is the sunlight. The lambda particle is the flower. The Star collaboration published their results in Nature in 2023. The paper describes the measurement of lambda-antilambda spin correlations in proton-proton and gold-gold collisions. The correlation was strongest in peripheral collisions, where the nuclei barely graze each other, because the magnetic field generated by the collision is strongest there. The alignment is then transferred to the real lambdas. It is not inert. This opens a new window into the quantum vacuum. Physicists can now probe the vacuum using high-energy collisions as a microscope. They can measure the spin structure of the vacuum. They can test whether the vacuum has preferred directions. They can ask whether the vacuum is the same everywhere, or whether it changes depending on the environment. It is an experimental subject. What the Star collaboration observed is not the end of the story. It is the beginning of a new way to interrogate the vacuum itself. Because if virtual strange quarks leave their spin imprinted on real lambdas, the question shifts from do virtual particles exist to what is the vacuum made of? This is where the quieter truth becomes unsettling. It has a spectrum, it has correlations, it has a spin structure, and if you can measure that structure, the RHIC experiment looked at strange quarks. But the vacuum contains virtual copies of every particle in the standard model. Virtual electrons, virtual muons, virtual top quarks, virtual Higgs bosons. Each one flickers with a different lifetime, a different mass, a different set of quantum numbers. The implications for cosmology are staggering. If the vacuum has structure, it is a sum over all the virtual particles that could exist. The standard calculation predicts a vacuum energy density 1020 to 0.0 times larger than what we observe. It is called the cosmological constant problem, and it has haunted theorists since the 1960s. But it does something equally important. It shows that the vacuum is not a black box. It is a system with measurable properties. There is another path forward, one that does not rely on perturbation theory at all. Lattice gauge theory places the entire calculation on a discrete grid of space-time points. No virtual particles, no Feynman diagrams. Just the fundamental fields evolving on a lattice. The Casimir force. The mass of the proton, all calculated without ever invoking a single virtual particle. This is the mathematical alternative that some physicists argue proves virtual particles are not fundamental. But the RHIC data complicates that argument. Lattice gauge theory can calculate the spin correlation between lambdas. It can reproduce the numbers. But it cannot explain why the correlation exists. The two descriptions are dual. The question is which one reveals the deeper truth. The lattice says the vacuum is a fluctuating field. The Feynman diagram says the vacuum is a sea of virtual particles. Neither is complete. Virtual particles are not real in the same way a chair is real. But they are not unreal in the way a hallucination is unreal. You cannot point to a relationship. But you can measure its effects. You can see how it changes the behavior of the people involved. The spin correlation between lambda and antilambda is the measurable effect of a relationship between 2 points in the quantum field. It is a bridge between the mathematics and the intuition. The deepest question is this: if the vacuum contains correlations that can become particles, the vacuum is the ground state of all quantum fields. But lowest does not mean simple. The vacuum of quantum chromodynamics, the theory of the strong force, is incredibly complex. It is not a desert. The RHIC experiment is the first expedition into that jungle with a compass that works. Perhaps the vacuum has a preferred direction. Perhaps the spin correlations we measure today are just the first hint of a much richer structure, a vacuum that is alive with patterns we have not yet learned to read. It is stranger than we can suppose. If this journey through the quantum vacuum left you thinking, consider this. The answer is not nothing. It is everything that could ever be.